How can we design photonic solar panels with photonic chip technology to generate way more energy than traditional solar panels and even operate photonic computing? This is a fascinating frontier where photonics, solar energy, and computing intersect. What are photonic solar panels? Traditional silicon solar panels convert only 15 to 22% of sunlight into electricity because silicon only absorbs a narrow band of the solar spectrum. Photons with energy above the band gap waste excess energy as heat. Sub-band gap photons pass through entirely unused. Photonic solar panels use structured light manipulation to overcome these limits. Core photonic technologies that boost solar efficiency. Photonic crystals, engineered periodic nanostructures that control how light propagates. In solar applications, they trap light inside the absorber layer far longer than conventional cells, redirect specific wavelengths to the most efficient absorber materials, enable spectral splitting, routing UV to one cell, visible to another, infrared to a third. Theoretical efficiency ceiling, 68% versus 29% for single-junction silicon. Plasmonics, metal nanoparticles, gold, silver, that resonate with specific light frequencies, creating intense local electric fields. They concentrate light into nanoscale volumes 100 to 1000 x ambient intensity. Couple sub-band gap photons into usable electron excitations. Enable ultra-thin solar cells, nanometers thick versus micrometers for silicon. Perovskite photonic hybrids. Perovskite semiconductors are naturally compatible with photonic nanostructuring, tunable bandgap by composition, high absorption coefficient when structured with photonic crystals, lab efficiencies already at 33% plus tandem designs. Perovskite plus silicon with photonic light management, projected 45 to 50%. Luminescent solar concentrators. Photonic waveguide panels that absorb diffuse light across a large area re-emitted at a specific wavelength. Concentrate it to small high-efficiency cells at the edges. Can work on windows, walls, and curved surfaces. Quantum dots, semiconductor nanocrystals with size-tunable bandgaps that perform photon-down conversion. 1 UV photon, 2 IR photons perform photon-up conversion. 2 IR photons, 1 visible photon. Harvest parts of the spectrum silicon completely ignores can be printed onto existing panels as a coating. Photonic chip integration. This is where things get truly revolutionary. Photonic integrated circuits, PICs, on solar panels could power conditioning at the speed of light, replace bulky inverters with on-chip. Photonic power converters eliminate resistive losses in copper wiring, route energy optically before final electrical conversion. On-panel intelligence. Embedded photonic chips perform real-time spectrum analysis, dynamically redirect wavelengths to optimal subcells, self-optimize for cloud cover, angle, and temperature changes. Photonic computing powered by the panel itself. Excess photons not converted to electricity feed directly into optical neural networks. The panel becomes both power source and processor. Tasks like weather prediction, grid optimization, and image recognition run at femtojoule energy costs. What photonic computing gains from solar integration? Zero-cost light source. The sun replaces laser diodes. Thermal co-management. Computing waste heat assist. Panel thermal regulation. Edge AI at scale. Millions of panels become a distributed computing network. Key research frontiers to watch. MIT's nanophotonic solar concentrators, achieving spectrum splitting at nanoscale. Stanford's perovskite silicon tandems with photonic texturing, 33.7% certified efficiency. Light emitter and luminous computing, photonic chips ready to integrate with energy harvesting. IBM's photonic packaging, chip-scale light routing that could be embedded in panel substrates. EU's Pepperoni project, specifically targeting photonic enhanced perovskite solar. A fully realized photonic solar panel with integrated photonic computing would convert 40 to 55% of sunlight to useful energy, versus 22% today. Use excess photons for optical computation at near zero energy cost. Form a distributed intelligence network across solar farms. Potentially pay for computing infrastructure essentially for free using otherwise wasted light. This is one of the most exciting convergences in green technology, where energy generation and information processing merge into a single photonic system. The physics supports it. The engineering challenges manufacturing at scale with sufficient precision and at low enough cost. Photonic solar panels and photonic computing, designing the next generation of energy and intelligence. The silicon solar panel, for all its remarkable success in transforming the global energy landscape, is approaching the ceiling of what its underlying physics will allow. Conventional photovoltaic technology converts sunlight into electricity through a fundamentally limited process. A semiconductor absorbs photons above a specific energy threshold and wastes the rest, either as heat or as unabsorbed radiation that passes straight through. The theoretical maximum efficiency of a single-junction silicon solar cell, known as the Shockley-Queisser limit, is approximately 29%, and commercial panels today achieve between 22% and 24%. The gap between what silicon panels capture and what the sun actually delivers represents an enormous, largely untapped reservoir of energy. Photonic technology offers a pathway beyond this limit. By engineering materials and structures at the nanoscale to control how light propagates, is absorbed, re-emitted, and converted, photonic solar panels can in principle harvest far broader swaths of the solar spectrum with far greater efficiency. More remarkably still, the same photonic technologies that enhance solar energy harvesting are converging with the emerging field of photonic computing, the use of light rather than electrons to perform computation, to create a vision of solar panels that are simultaneously power generators and information processors. This essay explores in depth how photonic solar panels work, the specific technologies that make them possible, how they can be integrated with photonic chip technology, and what a fully realized photonic energy computing system would look like and deliver, the limits of silicon and the promise of photonics. To understand why photonic solar panels represent such a significant advance, it is necessary to first understand precisely why conventional silicon panels are limited. Sunlight arrives at Earth's surface as a broad spectrum of electromagnetic radiation, spanning ultraviolet wavelengths below 400 nanometers, the visible spectrum from 400 to 700 nanometers, and the near and mid-infrared spectrum extending beyond 700 nanometers. Silicon has a band gap energy, the minimum photon energy required to excite an electron and generate current, corresponding to light at approximately 1100 nanometers. This single band gap creates two fundamental inefficiencies. Photons with wavelengths shorter than 1100 nanometers, that is, most of the visible and ultraviolet spectrum, have more energy than the band gap requires. Silicon absorbs them, but all the excess energy above the band gap is immediately dissipated as heat rather than converted to electricity. Photons with wavelengths longer than 1100 nanometers, a significant portion of the infrared spectrum, have less energy than the band gap requires and are simply not absorbed at all, passing through the cell unused. The net result is that a silicon panel under standard test conditions can convert at most about 29% of incident solar energy to electricity, and in practice achieves considerably less. Photonics addresses these limitations not by changing the semiconductor, but by controlling what happens to light before, during, and after it interacts with the absorbing material. Photonic structures can split the solar spectrum into components matched to different absorbers, concentrate light into tiny volumes to increase absorption probability, recycle photons that would otherwise escape, convert photons from unhelpful wavelengths to useful ones, and guide light along precise paths with minimal loss. These capabilities, applied systematically, can push solar cell efficiency toward theoretical limits that far exceed what silicon alone can achieve, up to 68% for concentrating multi-junction architectures, and potentially beyond for quantum enhanced designs. Core photonic technologies for solar enhancement. Photonic crystals. Photonic crystals are periodic nanostructures, arrays of features with dimensions on the order of the wavelength of light, that create what physicists call a photonic band gap. Just as a semiconductor's electronic band gap forbids electrons of certain energies, a photonic crystal's band gap forbids photons of certain wavelengths from propagating through it in specific directions. By engineering the geometry and composition of photonic crystals, designers can create structures that reflect specific wavelengths back into an absorber layer, trap light through multiple internal reflections to dramatically increase the effective optical path length, and route different wavelengths to different regions of a multi-junction cell stack. The light trapping function of photonic crystals is particularly significant. In a conventional solar cell, the thickness of the absorbing layer determines both how much light is absorbed and how much recombination of electron-hole pairs occurs. Thicker cells absorb more light but also lose more carriers to recombination. Photonic crystal back reflectors can trap light so effectively that an ultra-thin absorber layer achieves the same optical absorption as a much thicker conventional layer, dramatically reducing recombination losses. Theoretical calculations suggest that perfect photonic crystal light trapping can increase absorption by a factor of 4 n to the power of 2, where n is the refractive index of the absorber, a factor of more than 50 for silicon. In practice, Photonic crystal texturing has been shown to improve thin-film solar cell efficiency by 20 to 30% in laboratory conditions. Spectral splitting through photonic crystals takes the concept further. By designing a photonic crystal that reflects infrared light while transmitting visible light, or vice versa, it becomes possible to route different portions of the solar spectrum to different solar cells optimized for those wavelengths. A stack of 2 or 3 such cells, each tuned to a different spectral range and separated by wavelength-selective photonic crystal mirrors, constitutes a multi-junction cell architecture that can capture far more of the solar spectrum than any single junction device. Plasmonics. Plasmonics exploits the collective oscillation of electrons at the surface of metallic nanoparticles, a phenomenon called a localized surface plasmon resonance, to create intense concentrations of electromagnetic field in the immediate vicinity of the particle. When light at the resonant frequency of the plasmon strikes a gold or silver nanoparticle, the resulting electric field enhancement can be 100 to 1000 times the intensity of the incident light in the near-field region around the particle. This extraordinary concentration of optical energy has several important applications in solar cells. First, plasmonic nanoparticles embedded in or near a solar cell's absorbing layer dramatically increase the probability that an incoming photon will be absorbed, enabling the use of thinner and less expensive absorber layers without sacrificing performance. Second, plasmons can couple light into guided modes in thin semiconductor films, effectively turning the absorber layer into a waveguide that traps photons for extended interaction times. Third, and most innovatively, hot electrons generated by plasmon decay, electrons with energies well above the semiconductor band gap, can in principle be extracted before they thermalize, capturing energy that would normally be lost as heat. Hot carrier solar cells based on plasmonic nanostructures represent one of the most promising pathways to exceeding the Shockley-Queisser limit, with theoretical efficiencies above 60%. The practical challenges of plasmonics in solar cells include optical losses and the metal nanoparticles themselves, the difficulty of positioning particles with nanometer precision at scale, and the extremely short time scale, femtoseconds, available for hot electron extraction before thermalization. Nevertheless, plasmonic coatings have already demonstrated meaningful efficiency improvements in laboratory thin film cells, and manufacturing techniques for nanoparticle deposition are advancing rapidly. Perovskite photonic hybrids. Perovskite semiconductors, a class of materials with a characteristic crystal structure first identified as solar cell absorbers in 2009, have emerged as the most exciting photovoltaic material discovery of the past 2 decades. Their band gap can be tuned across much of the visible and near-infrared spectrum by varying their chemical composition, their absorption coefficient is extremely high, and their carrier diffusion lengths are remarkably long for solution. Processed materials. Laboratory perovskite single-junction cells have already achieved certified efficiencies of over 26%, approaching the silicon theoretical limit after just 15 years of development. When perovskite absorbers are combined with photonic nanostructuring, the results are striking. Photonic crystal texturing of perovskite films enhances light trapping in the thin absorber layers that perovskite's high absorption coefficient allows, further improving efficiency. More significantly, perovskite's tunable band gap makes it the ideal top cell material for tandem architectures paired with silicon or other lower band gap materials. In a perovskite silicon tandem, the perovskite top cell absorbs high-energy visible photons, while the silicon bottom cell captures the near-infrared photons transmitted through the perovskite, with photonic interlayer design optimizing light management at the interface between the two cells. Certified efficiencies of 33.7% have already been achieved in laboratory devices, and theoretical modeling projects that optimized photonic management could push tandem efficiencies toward 45 to 50%. This would represent more than double the performance of today's commercial silicon panels. Luminescent solar concentrators. Luminescent solar concentrators represent a fundamentally different approach to photonic solar energy harvesting, one that addresses not just efficiency, but also the challenge of integrating solar harvesting into built environments where conventional panels are impractical. An LSC consists of a transparent or semi-transparent waveguide, typically a glass or polymer slab, doped with luminescent molecules or quantum dots that absorb sunlight and re-emit it at a longer wavelength. The re-emitted photons are trapped within the waveguide by total internal reflection and guided to small high-efficiency solar cells mounted at the edges of the slab. The efficiency advantage of LSCs lies in their ability to concentrate diffuse light, the scattered illumination that makes up a substantial fraction of sunlight in cloudy climates and reaches surfaces at all angles, as well as direct sunlight. Conventional concentrating optics require direct sunlight and must track the sun mechanically to maintain focus. LSCs work equally well with diffuse light, require no moving parts, and can be made partially transparent, enabling their integration into windows, building facades, greenhouse glazing, and vehicle surfaces. The photonic engineering of LSC waveguides, including the design of luminescent species with near-unity quantum yield, large Stokes shifts that minimize reabsorption losses, and spectral properties matched to high-efficiency edge cells, is an active and productive research area, with large-area LSC panels now demonstrating overall system efficiencies approaching 10% even under diffuse illumination conditions. Quantum dots and photon management. Quantum dots are semiconductor nanocrystals whose electronic and optical properties are determined by their physical size rather than solely by their chemical composition, a consequence of quantum confinement effects that emerge when a semiconductor's dimensions approach the de Broglie wavelength of its charge carriers. By controlling the size of quantum dots during synthesis, their absorption and emission spectra can be precisely tuned across the entire solar spectrum. This tunability makes them uniquely powerful tools for photon management in solar cells. Two photon management processes enabled by quantum dots are particularly significant for solar applications. Photon down conversion, also called quantum cutting, allows a single high-energy ultraviolet photon to be converted to two lower-energy photons that can each generate one electron-hole pair in a silicon cell. Since ultraviolet photons represent a small but significant portion of solar irradiance that conventional silicon cells handle inefficiently, quantum dot down conversion coatings applied to the front surface of existing silicon panels can improve their efficiency without any modification to the underlying cell. Photon up conversion works in the opposite direction, combining two sub-band gap infrared photons to produce a single visible photon that silicon can absorb. Since sub-band gap infrared radiation accounts for roughly 20% of the solar energy that silicon panels currently waste entirely, up conversion layers on the rear surface of silicon cells represent a significant untapped efficiency opportunity. Quantum dot up conversion layers have already demonstrated meaningful photocurrent enhancements in laboratory conditions, and the development of solution processable quantum dot inks that can be applied to existing panels as coatings represents a commercially attractive pathway to near-term efficiency gains. Photonic chip technology and its integration with solar panels. What photonic integrated circuits do? A photonic integrated circuit performs operations on light, guiding, splitting, modulating, detecting, and interfering optical signals, using structures fabricated on a chip substrate, analogously to how an electronic integrated circuit processes electrical signals using transistors and interconnects. The substrate is typically silicon or silicon nitride, both of which are transparent at telecommunications wavelengths and highly compatible with established semiconductor fabrication processes. Waveguides etched into the chip surface confine and guide light with extremely low loss. Microring resonators, Mach-Zehnder interferometers, and grating couplers perform filtering, modulation, and coupling functions with femtojoule energy consumption per operation, orders of magnitude more efficient than their electronic equivalents for many signal processing tasks. The primary advantage of photonic integrated circuits over electronic ones for computing and communications is speed combined with low energy dissipation. Photons travel at the speed of light and do not interact with each other in linear media, meaning that multiple optical signals can be transmitted simultaneously through the same waveguide at different wavelengths without interference, a phenomenon called wavelength division multiplexing. The energy required to transmit a bit of information optically is already far lower than electrically over distances greater than a few centimeters. And for computational operations involving large matrix multiplications, the dominant operation in neural network inference, optical approaches offer potential energy savings of 3 to 4 orders of magnitude compared to electronic hardware. Integration with solar panel architecture. The integration of photonic chips with solar panel architecture operates on two distinct levels. At the power conditioning level, photonic chips can replace or augment conventional electronic power electronics. The conversion of photovoltaic DC electricity to grid-compatible AC, currently performed by inverters that introduce resistive losses and require bulky magnetic components, can in principle be assisted by photonic power converters that manage energy routing with lower loss and greater precision at the chip level. More significantly, the optical interconnects of photonic chips can route signals between panel subcells, monitoring circuits, and control systems without the resistive losses inherent in copper wiring, particularly important in large-scale installations where wiring losses accumulate significantly. At the functional integration level, photonic chips embedded in the panel substrate can perform real-time spectral analysis of incident light, dynamically adjusting the optical routing within a multi-junction cell stack to optimize energy capture as solar angle, atmospheric conditions, and cloud cover change throughout the day. An embedded photonic chip can measure the spectral composition of incoming light on microsecond timescales and adjust tunable photonic crystal filters or electro-optic elements to route each wavelength component to the sub-cell where it will be most efficiently converted. This dynamic spectral optimization, impossible with passive optical structures, could recover a significant fraction of the efficiency losses that result from the mismatch between fixed optical designs and the continuously varying solar spectrum. Photonic computing powered by solar panels. The most radical dimension of photonic solar panel technology is the possibility of using the panels themselves as both power source and optical computing platform. Conventional computing hardware, whether silicon CPUs, GPUs, or AI accelerators, consumes electricity and generates heat. Photonic computing hardware uses light to perform computations, consuming far less energy and generating far less heat. The sun provides an essentially free and inexhaustible source of photons. The convergence of these facts suggests a system architecture in which photons that cannot be efficiently converted to electricity, due to spectral mismatch, geometric losses, or saturation of the absorbing material, are instead coupled directly into an on-panel photonic computing core, where they perform useful computation at near zero marginal energy cost. In practice, this integration would work as follows. The photonic crystal layer at the front of the panel separates incoming sunlight by wavelength. Wavelengths matched to the solar cell subcells are routed to the absorbers for electricity generation. Wavelengths that fall in gaps between the subcell absorption bands, which would otherwise be wasted, are instead coupled into waveguides that feed an on-chip photonic neural network or optical signal processor. This processor performs inference tasks, weather prediction, grid load forecasting, fault detection, image recognition for environmental monitoring, using the free photons as its computational resource. The electrical output of the solar cell powers the detector arrays and readout electronics that extract the results of the optical computation. The scale implications of this architecture are profound. A solar farm of 100 megawatts might consist of several 100,000 individual panels. If each panel hosts an on-chip photonic computing core, the aggregate computational capacity of the farm could be enormous. A distributed optical supercomputer powered essentially for free by the portions of sunlight that conventional photovoltaics cannot use. The communication between panels in such a network could itself be optical, using free space laser links or optical fiber connections between panel clusters, creating a high bandwidth, low latency distributed computing fabric embedded in the energy infrastructure. System architecture, from photon to power to computation. A fully integrated photonic solar computing system would embody the following layered architecture, from the outermost surface of the panel to the computing infrastructure it supports. The first layer is a broadband anti-reflection and photon management coating, incorporating quantum dot-down conversion materials that convert ultraviolet photons to the visible range and plasmonic nanostructures that scatter incoming light at angles, optimizing coupling into the underlying cell layers. This layer ensures that the maximum possible fraction of incident solar photons enters the active region of the panel rather than being reflected away. The second layer is the photonic crystal spectral splitter, a nanostructured film that separates incoming light into spectral bands matched to the subcells below. High-energy visible photons are transmitted to the top subcell, lower-energy near-infrared photons are reflected downward to the bottom subcell. Photons in the spectral gaps between sub-cell absorption bands are deflected laterally into waveguides that route them to the photonic computing core at the panel edge or substrate. The third layer is the multi-junction photovoltaic stack, most likely a perovskite top cell over a silicon bottom cell, with photonic interlayer texturing optimizing light management at the interface. This stack converts the spectrally sorted photons delivered by the layer above into electricity with efficiency approaching the theoretical tandem limit. The fourth layer is the photonic integrated circuit substrate, fabricated on or bonded to the back surface of the photovoltaic stack. This chip integrates optical waveguides that receive the computing photons from the spectral splitter layer, a photonic neural network core that performs matrix multiplication operations optically. Photodetector arrays that read out the results of optical computations, electronic control circuits powered by the photovoltaic stack that manage the optical routing and interface to external systems, and power conditioning circuits that manage the electrical output of the solar cells. The fifth and outermost layer of the system architecture is the interpanel network. Optical fiber connections between panels, or free space optical links across the panel array, connect the individual photonic computing cores into a distributed processing network. This network can perform computations too large for a single panel, share model weights across the array, and communicate results to a central aggregation point for delivery to users or for local autonomous control of the energy system. Performance projections and current state of development. The efficiency gains achievable through photonic solar panel technology, while still largely in the research and early development phase, are supported by well-established physics and demonstrated laboratory results. Single-junction silicon cells with photonic crystal light trapping have demonstrated efficiencies approaching 26% in laboratory conditions, compared to the 22 to 24% of commercial panels. Perovskite silicon tandem cells with photonic light management have achieved certified efficiencies of 33.7%, a figure that was unthinkable for photovoltaics a decade ago. Theoretical modeling of optimized multi-junction photonic solar cells with quantum dot spectrum management projects efficiencies of 45 to 50% for 3-junction devices and potentially higher for more complex stacks. The photonic computing component of the integrated system is also advancing rapidly. Photonic integrated circuits for AI inference have been demonstrated by companies including Lightmeter, Luminous Computing, and Intel, with energy consumption per multiply accumulate operation already below 1 picojoule and projected to reach the femtojoule range as fabrication precision improves. The integration of photonic chips with solar substrates has not yet been demonstrated in a production device, but the individual technologies, photonic chip fabrication on silicon substrates, bonding of photonic layers to photovoltaic stacks, waveguide coupling between optical layers, are all established capabilities that have been demonstrated in research contexts. The key manufacturing challenge is precision and cost. Photonic nanostructures require feature sizes of tens to hundreds of nanometers, demanding fabrication processes, electron beam lithography, nanoimprint lithography, atomic layer deposition, that are currently more expensive than conventional solar panel manufacturing. Nanoimprint lithography, which uses a master template to stamp nanostructures into large areas rapidly and cheaply, is the most promising pathway to cost-competitive photonic solar panels at scale. As the technology matures and manufacturing volumes increase, the cost premium of photonic nanostructuring is expected to fall substantially, following the same learning curve that drove silicon panel costs down by 90% over the past decade. Environmental and civilizational implications. The implications of photonic solar panels with integrated photonic computing extend far beyond incremental improvements in energy conversion efficiency. They represent a potential phase transition in how human civilization generates and uses energy and information. On the energy side, doubling or tripling the efficiency of solar panels means that the same land area can generate 2 to 3 times as much electricity, dramatically reducing the land footprint of renewable energy deployment. For a world that must simultaneously expand clean energy production and protect natural ecosystems, this efficiency gain is not merely economical, it is ecologically significant. Higher efficiency also reduces the material intensity of solar energy, lowering the demand for silicon, glass, aluminum, and other materials per unit of energy generated, reducing the environmental footprint of the manufacturing process itself. On the computing side, the integration of photonic computing into the solar energy infrastructure creates the possibility of a fundamentally new paradigm for distributed intelligence. Today, artificial intelligence and large-scale data processing are concentrated in energy-intensive data centers that themselves require enormous amounts of electricity, a growing fraction of total global power consumption. A world in which millions of solar installations host distributed photonic computing cores, powered by the free photons that conventional cells cannot use, could perform a large fraction of humanity's computational work at near zero incremental energy cost. This convergence of clean energy and efficient computing could simultaneously address 2 of the most significant sustainability challenges of the 21st century. Furthermore, the sensing and monitoring capabilities of photonically integrated solar arrays could transform environmental management. Each panel, equipped with photonic spectral analysis capabilities, becomes a node in a planetary sensor network, monitoring atmospheric composition, solar irradiance, temperature, and other environmental parameters in real time at spatial resolutions and geographic coverages, currently impossible with existing monitoring infrastructure. The data generated by this network, processed by the on-panel computing cores and aggregated through the inter-panel optical network, could provide an unprecedented real-time picture of Earth's environmental systems, enabling faster and more effective responses to pollution, climate change, and ecosystem degradation. Photonic solar panels with integrated photonic computing represent one of the most ambitious and consequential technological visions of the coming decades. By applying the full toolkit of nanophotonic engineering, photonic crystals, plasmonics, perovskite photonic hybrids, luminescent concentrators, quantum dots, and photonic integrated circuits, to the problem of solar energy harvesting and utilization, it becomes possible to envision panels that convert 40 to 55% of incident sunlight to useful energy, compared to the 22% of today's best commercial products, while simultaneously performing optical computation at near zero marginal energy cost, using photons that conventional cells cannot absorb. The physics of these technologies is well established. The laboratory demonstrations are encouraging and rapidly advancing. The engineering challenges, precision and fabrication at panel scale, reliable long-term operation of organic and nanostructured materials, integration of photonic chips with photovoltaic substrates, are substantial but not insurmountable, and each is the subject of intensive research investment worldwide. The cost curves for the underlying technologies are moving in the right direction. What photonic solar panels ultimately promise is not merely better solar panels, but a new class of infrastructure, one that simultaneously harvests energy, processes information, monitors the environment, and communicates across networks, all powered by the most abundant and universally available energy source on Earth. In a world urgently seeking both clean energy and sustainable computing, photonic solar technology stands at the intersection of both needs, offering a path toward a future in which the sun provides not just the power to run our civilization, but the light to think with as well. How can we build extremely sustainable cities powered by photonic energy and computing systems? The core vision, a photonically powered smart city. A photonically powered sustainable city operates on three integrated layers: energy layer, photonic solar infrastructure generating abundant clean power computing layer, distributed photonic chips processing city data at near zero energy cost urban layer, buildings, transport, water, and food systems designed around photonic abundance. Energy infrastructure, building integrated photonic solar. Every surface becomes a power generator: facades, windows, LSC glazing, rooftops, roads, and pavements embed photonic solar materials. Smart glass, using electrochromic plus LSC technology, simultaneously harvests energy and controls clear heat. Photonic solar roads with quantum dot coatings generate power while surviving vehicle loads. Vertical photonic farms on building faces use perovskite photonic tandems tuned for diffuse urban light. City-scale energy grid. Photonic microgrids connect buildings optically, reducing transmission losses. AI-optimized distribution using on-panel photonic computing balances supply-demand, and real-time underground thermal storage paired with solar thermal photonic collectors provides 24/7 energy security. Vehicle 2. Grid integration with electric fleets acting as distributed storage. Photonic computing infrastructure, distributed intelligence network. Every building's photonic solar panels double as computing nodes. Citywide optical fiber mesh connects nodes into a planetary scale distributed supercomputer. Edge photonic AI processes traffic, utilities, weather, and emergency data locally with microsecond response. No centralized data center needed. Computing is embedded in the energy infrastructure itself. Urban digital twin, real-time photonic sensor networks, LiDAR, spectroscopic, thermal, feed a living 3D model of the city. AI predicts and prevents infrastructure failures, optimizes energy flows, and models disaster scenarios. Citizens interact with the digital twin for navigation, services, and civic participation. Buildings and architecture, zero-energy building design. Passive solar architecture oriented to maximize photonic panel exposure. Aerogel insulation and vacuum glazing minimize heat loss to near zero. Phase change materials in walls store and release thermal energy, reducing HVAC demand by 70%. Biomimetic ventilation, inspired by termite mounds, provides natural cooling without electricity. Living buildings, green roofs and walls integrated with photonic panels. Vegetation provides cooling. Panels provide power. Building integrated water harvesting from fog, rain, and atmospheric moisture using photonic humidity sensors. Self-healing concrete with embedded sensors reduces maintenance and extends building lifespans to 200+ years. Mycelium-based insulation and hempcrete walls sequester carbon while providing structure. Transport systems, zero-emission mobility, autonomous electric vehicle fleets powered by photonic grid, eliminating private car ownership. Hyperloop corridors between city districts powered entirely by solar photonic strips along tube surfaces. Solar photonic drone networks for last-mile delivery and emergency services. Electric waterways in canal cities powered by floating photonic panels. Smart traffic and flow. Photonic computing nodes optimize traffic flow citywide with zero congestion. As a design goal, pedestrian priority urban design with 15. My new neighborhood planning eliminates most motorized trips, elevated walkways and cycling. Superhighways physically separate active transport from vehicle lanes. Water and food systems. Closed-loop water. Atmospheric water generation powered by photonic solar harvest moisture from air. Photocatalytic water purification using titanium dioxide activated by solar photons purifies water without chemicals. Gray water recycling loops in every building. Managed by photonic sensor networks. Real-time contamination detection using photonic spectroscopy in water mains. Urban food production. Vertical farms powered by photonic solar use tuned LED spectra for maximum crop yield per watt. Rooftop aquaponics integrates fish farming and plant growing in closed nutrient loops. AI optimized growing using photonic hyperspectral imaging to monitor plant health at cellular level. Insect protein facilities convert food waste to protein with 100x less land than conventional livestock. Waste and circular economy. Photonic sorting robots identify and separate every material stream with 99% plus accuracy. Plasma gasification converts residual waste to syngas and clean electricity. Chemical recycling hubs powered by photonic solar break down plastics to monomers. Zero landfill policy enforced through digital product passports tracking every material. Governance and social systems. Photonic civic infrastructure. Distributed ledger systems run on photonic computing for transparent, tamper-proof governance. Real-time participatory budgeting platforms allow citizens to direct city spending. AI-assisted policy simulation tests new regulations in the digital twin before real-world implementation. Universal basic energy. Abundant photonic power makes energy essentially free for all residents. Biophilic design 40% green space minimum woven through all districts. Wildlife corridors connecting parks and green roofs into an urban ecosystem network. Dark sky zones using smart photonic lighting items to near zero between midnight and dawn. Acoustic refuges, areas engineered for near silence using photonic noise monitoring and active cancellation. The three cities leading this vision today. Masdar City, UAE, purpose-built zero-carbon city, though still incomplete. Songdo, South Korea, fully sensor-integrated smart city with pneumatic waste systems. Copenhagen, Denmark, targeting carbon neutrality by 2025. Cycling. First design. The full photonic city vision integrates all of these precedents and takes them a generation further, where the energy system and the computing system are the same system, embedded in every surface of the built environment. Building extremely sustainable cities powered by photonic energy and computing systems. The city is humanity's most consequential invention. More than half the world's population now lives in urban areas, and that proportion is projected to reach 2/3 by 2050. Cities consume roughly 75% of global energy, generate approximately 70% of global carbon dioxide emissions, and concentrate the environmental stresses of modern civilization. Air and water pollution, waste generation, heat island effects, and biodiversity loss, into dense, complex systems that are simultaneously the source of civilization's greatest achievements and its most acute environmental problems. How we design and power our cities in the coming decades will determine, more than any other single factor, whether humanity achieves a sustainable relationship with the natural systems on which it depends. The emergence of photonic energy and computing systems, technologies that harness, manipulate, and compute with light, opens a fundamentally new design space for sustainable urban environments. Photonic solar panels capable of converting 40 to 55% of incident sunlight into useful energy, integrated with photonic computing chips that perform artificial intelligence and data processing at near zero marginal energy cost. make possible a city that is not merely less damaging than its predecessors but genuinely regenerative, one that produces more energy than it consumes, processes its data using the very light that powers it, monitors and manages its own systems in real time, and provides its residents with the quality of life that conventional cities cannot match at any level of resource consumption. This essay develops a comprehensive vision of such a city, its energy infrastructure, computing architecture, built environment, transport systems, food and water systems, waste management, and governance, and examines both the technological foundations that make it achievable and the design principles that should guide its development. The photonic energy infrastructure, building integrated photonic solar. The foundational shift in a photonically powered city is the reconception of every built surface as a potential energy harvesting element. Conventional cities concentrate solar energy generation in dedicated installations, rooftop arrays, solar farms on the urban periphery, that account for a small fraction of total urban surface area. A photonic city distributes energy generation across every facade, window, roof, road surface, and public space, transforming the built environment itself into a continuous power plant. The technologies that make this possible are the photonic solar innovations described in the preceding essay in this series: luminescent solar concentrator glazing that harvests energy across window surfaces while remaining partially transparent; perovskite photonic tandem cells optimized for the diffuse, low-angle light characteristic of vertical building facades in temperate latitudes; quantum dot coatings that can be applied to existing glass, concrete, and polymer surfaces to add energy harvesting capability without structural modification; and photonic crystal-enhanced thin-film solar materials that can be laminated onto road surfaces, pavement tiles, and structural panels. The aggregate generating capacity of a city that deploys these technologies across all available surfaces is enormous. Studies of solar resource availability in dense urban environments consistently show that building integrated photovoltaics alone could, in principle, supply 50 to 100% of a city's electricity demand if deployed on all available surfaces with sufficiently high efficiency, a threshold that photonic solar technologies can reach. Smart glass represents one of the most transformative single technologies in this vision. Current electrochromic smart glass can switch between transparent and opaque states to control solar heat gain, reducing cooling load significantly. The next generation of photonic smart glass integrates luminescent solar concentration, electrochromic control, and photonic spectral filtering in a single glazing unit that simultaneously harvests energy, controls glare and heat, and modulates visible light transmission in response to occupant preferences and building energy management commands. Every window in the city becomes an active energy and comfort management element rather than a passive aperture. The city-scale photonic energy grid. The distribution of energy generation across the built environment requires a correspondingly distributed and intelligent grid architecture. The conventional model of large centralized power plants transmitting electricity over long distances to passive consumers is replaced in the photonic city by a network of prosumers, buildings and infrastructure elements that both generate and consume energy, connected by a smart microgrid that balances supply and demand in real time. The photonic computing cores, embedded in the city's solar panels, play a central role in this grid management. Each panel's on-chip photonic processor monitors its own generation, communicates with neighboring panels and building energy management systems through the city's optical fiber network, and contributes to a city-wide AI optimization of energy flows that operates on millisecond timescales, far faster than human operators or conventional SCADA systems can manage. This distributed intelligence enables the grid to respond instantaneously to clouds passing over solar arrays, to sudden changes in building demand, and to fluctuations in the output of individual panels without any central control intervention. Energy storage is the complement to this distributed generation and intelligence. The photonic city deploys storage at multiple scales: lithium-ion or next-generation solid-state batteries at the building level for hourly balancing, grid-scale iron or flow batteries at the district level for daily balancing, underground thermal energy storage systems, aquifer thermal energy storage, pit thermal energy storage, or phase change material tanks, for seasonal balancing, and the electric vehicle fleets that serve the city's transport system as a vast, continuously available distributed storage resource. The integration of all these storage assets into the photonic grid management system, optimized by AI running on the city's embedded photonic computing infrastructure, creates a resilient, self-balancing energy system capable of maintaining near 100% renewable supply reliability across all weather conditions and seasons. The photonic computing architecture, distributed optical intelligence. In a conventional city, computing infrastructure is concentrated in data centers, large buildings filled with energy-intensive electronic servers, cooled by equally energy-intensive mechanical systems, connected to the urban fabric by fiber optic and wireless networks. These data centers consume growing fractions of total electricity supply and represent significant single points of failure for the digital services that modern urban life depends upon. The photonic city replaces this centralized model with a radically distributed computing architecture in which photonic chips embedded in solar panels, building management systems, transport infrastructure, and utility networks collectively constitute a city-wide optical computing fabric of enormous aggregate capacity. The key enabling inside is that photonic computing chips can perform their operations using the same photons that the city's solar infrastructure is already handling, specifically, the portions of the solar spectrum that cannot be efficiently converted to electricity but can be coupled into optical waveguides and used to perform matrix multiplications in optical neural networks. In this architecture, there is no separate energy cost for computing. The computational resource is a byproduct of energy harvesting, using light that would otherwise be wasted. The city's computing capacity is thus a free co-product of its energy system, scaling automatically as the energy infrastructure grows. The distributed photonic computing fabric processes the enormous streams of data generated by the city's sensor networks, traffic flows, energy consumption, air quality, water quality, structural health, emergency events, weather conditions, at the edge, where the data is generated, rather than transmitting raw data to distant servers for processing. This edge computing architecture dramatically reduces communication bandwidth requirements and latency, enabling real-time responses to dynamic urban conditions. Traffic signals adjust within milliseconds to actual vehicle and pedestrian flows. Building energy management systems respond instantaneously to occupancy changes. Water system pressure is continuously optimized across the distribution network. Emergency services are dispatched before human dispatchers have finished reading the first incident report. The urban digital twin. The distributed photonic computing infrastructure underpins the city's most powerful planning and management tool, a continuously updated, real-time digital twin, a comprehensive computational model of the city in its entirety, encompassing every building, infrastructure element, vehicle, utility network, and environmental condition, fed by the city's sensor networks and updated in real time by the photonic computing fabric. The digital twin provides planners, operators, and citizens with an unprecedented window into the city's functioning. The value of the digital twin extends far beyond operational management. It enables predictive maintenance of infrastructure, identifying a bridge bearing approaching failure, a water main showing signs of corrosion, a power transformer operating outside its design parameters before failures occur, eliminating the disruption, danger, and expensive reactive repairs. It enables scenario modeling. Planners can test the impact of a new transit line, a zoning change, a flood protection measure, or a public health intervention in the virtual city before committing resources in the physical one. It enables participatory governance. Citizens can interact with the digital twin through accessible interfaces, exploring the likely consequences of proposed policies and contributing local knowledge to planning decisions. And it enables the optimization of the city as an integrated system, identifying synergies and conflicts between different infrastructure domains that would be invisible to planners working with each system in isolation. Buildings in the built environment. Zero and positive energy buildings. The buildings of the photonic city are designed from first principles to minimize energy demand and maximize energy generation, with the target of achieving positive energy balance, generating more energy over a year than they consume. This requires the integration of passive design strategies that reduce demand with active photonic systems that maximize supply. On the demand side, passive solar architecture orients buildings to maximize winter solar gain and minimize summer overheating, reducing heating and cooling loads dramatically. Aerogel insulation, an anomalous material with thermal conductivity lower than still air, achieves insulation performance in layers centimeters thick that conventional materials require tens of centimeters to match, enabling highly insulated envelopes without sacrificing floor area or architectural expression. Vacuum-insulated glazing provides window thermal performance approaching that of insulated walls, eliminating the cold surfaces and radiant discomfort that drive heating demand in conventionally glazed buildings. Phase-change materials integrated into wall and ceiling panels store and release thermal energy as they change between solid and liquid states, buffering internal temperatures against external swings and reducing HVAC system size and runtime. Biomimetic ventilation strategies, inspired by the passive cooling systems of termite mounds and other natural structures, use stack effect, cross-ventilation, and evaporative cooling to maintain comfortable temperatures without mechanical energy input across a wide range of climatic conditions. On the supply side, every available surface of the building envelope is integrated with photonic solar materials appropriate to its orientation, inclination, and lighting conditions. High-efficiency perovskite silicon tandem panels with photonic crystal light management cover south-facing roofs and high-angle surfaces. LSC glazing harvests energy from windows and skylights. Quantum dot coatings on east and west facades capture morning and afternoon sun. Building integrated photovoltaic cladding panels on north facades harvest diffuse sky radiation. The aggregate generating capacity of a well-designed photonic building in a temperate climate can exceed its annual energy consumption by a factor of 2 or 3. With the surplus fed to the district microgrid to supply neighbors whose generation is more limited. Living buildings in biophilic design. The Photonic City's buildings are not merely energy machines, they are living systems that integrate ecological function with human habitation. Green roofs, planted with native vegetation adapted to the local climate, provide stormwater retention, thermal insulation, urban biodiversity habitat, and cooling through evapotranspiration. Green walls on building facades reduce surface temperatures, improve air quality, provide habitat, and create the sensory richness of living surfaces that research consistently shows improves the psychological well-being of building occupants. When photonic solar panels are integrated with green roofs and walls, sharing structural support, electrical connections, and water management systems, the two technologies complement each other. Vegetation cools the panels, improving their efficiency, while the panels provide shade that supports the growth of plants that would otherwise struggle in full sun. The biophilic design principle, that human beings have an evolved need for connection with the natural world and function better in environments that provide it, extends beyond individual buildings to the urban fabric as a whole. The Photonic City targets a minimum of 50 square meters of accessible green space per resident, distributed throughout the urban fabric in parks, pocket gardens, school grounds, and green corridors rather than concentrated in large peripheral parks that most residents rarely visit. Wildlife corridors connecting green roofs, street trees, parks, and urban forests create a continuous ecological network through which insects, birds, and small mammals can move, supporting biodiversity levels far higher than conventional urban landscapes. Waterways, rivers, canals, retention ponds, bioswales, are restored or created as ecological arteries that also manage storm water, moderate microclimate, and provide spaces for human recreation and contemplation. Transport and mobility, the end of the private car. The private automobile is the most resource-intensive and space-consuming element of the conventional city. Cars occupy 30 to 50% of urban land area in the form of roads and parking. They are responsible for the majority of urban air pollution and a significant fraction of urban carbon emissions. They are involved in approximately 1.35 million fatalities globally each year, and they are parked, unused, more than 95% of the time. The Photonic City eliminates the private car not by prohibition, but by making car ownership economically irrational through the provision of superior alternatives. The core of the Photonic City's transport system is a network of autonomous electric vehicles, shared, on-demand, and continuously available, powered by the city's photonic grid. Because these vehicles are autonomous, they can be summoned instantly, pick up and drop off multiple passengers on optimized routes, return to charging facilities when not needed, and operate as mobile storage nodes for the grid during periods of high renewable generation. Because they are shared, the city requires perhaps 1/10 as many vehicles as a car-dependent city of equivalent population, freeing an enormous amount of land currently devoted to parking and wide arterial roads for buildings, parks, and active transport infrastructure. The photonic computing fabric optimizes the routing and dispatch of the vehicle fleet in real time, minimizing wait times, energy consumption, and road congestion simultaneously. Public transit, rail, tram, bus rapid transit, forms the high-capacity spine of the mobility network, with autonomous electric vehicles providing first and last-mile connections. Elevated cycling superhighways and pedestrian networks physically separated from vehicle traffic make active transport safe, comfortable, and attractive across all weather conditions. The 15-minute city planning principle, ensuring that every resident can access work, education, healthcare, retail, and recreation within a 15-minute walk or cycle from their home, minimizes the need for motorized travel altogether. Together, these elements reduce per capita vehicle kilometers traveled by 70 to 80% compared to car-dependent urban forms, with corresponding reductions in energy consumption, emissions, noise, and road casualties. Photonic infrastructure for mobility. The transport infrastructure of the photonic city is itself an energy and computing resource. Photonic solar strips along the surfaces of elevated rail and hyperloop corridors generate electricity from the large surface areas these structures present. Streetlights equipped with photonic solar panels and computing nodes simultaneously illuminate public spaces, harvest energy, monitor traffic and environmental conditions, and provide communications infrastructure for the city's sensor network. Electric vehicle charging infrastructure is integrated into the photonic microgrid, with smart charging algorithms that optimize the timing and rate of charging across the fleet to maximize the consumption of locally generated solar energy and minimize grid stress. Water systems. Closed-loop urban water. Water scarcity is an escalating global crisis, and cities are both major consumers of fresh water and major generators of water pollution. The photonic city addresses both dimensions through a closed-loop water architecture that harvests, purifies, distributes, uses, recycles, and repurifies water in continuous cycles with minimal net consumption of fresh water resources. Atmospheric water generation. The capture of water vapor from ambient air using hygroscopic materials or refrigerative condensation, powered by photonic solar electricity, provides a source of clean water that is independent of rainfall, rivers, or groundwater and available wherever the air contains moisture. Photocatalytic water purification, using titanium dioxide or other photocatalysts activated by solar photons, breaks down organic pollutants, pharmaceuticals, and pathogens in water through chemical oxidation, producing drinking quality water without the chemical inputs, chlorine, coagulants, pH adjusters, required by conventional water treatment. Photonic spectroscopy sensors distributed throughout the water distribution network monitor water quality in real time, detecting contamination events within seconds and enabling immediate isolation of affected sections before pollutants reach consumers. Gray water recycling systems in every building treat water from sinks, showers, and laundry for reuse in toilet flushing and irrigation, reducing potable water demand by 30 to 40%. Black water treatment systems recover nutrients, nitrogen and phosphorus, from sewage for use as agricultural fertilizer, closing the nutrient cycle that conventional sewage treatment breaks. Stormwater is managed through green infrastructure, bioswales, rain gardens, permeable paving, and green roofs that absorbs rainfall close to where it falls, recharging groundwater and reducing peak flows that overwhelm combined sewer systems. The aggregate effect of these systems is a city that recycles more than 95% of the water it uses, reducing dependence on external water sources to a small fraction of conventional urban water consumption. Food systems, urban food production at scale. The global food system is responsible for approximately 1/3 of total greenhouse gas emissions, is the leading driver of biodiversity loss, and depends on vast areas of agricultural land located far from the urban populations it serves, with corresponding transport energy costs and supply chain vulnerabilities. The photonic city internalizes a significant fraction of its food production within the urban fabric, using photonic technologies to achieve yields and resource efficiencies that conventional agriculture cannot approach. Vertical farms, multi-story growing facilities in which crops are cultivated under artificial lighting in stacked layers, achieve land use efficiencies 100 to 1,000 times higher than conventional agriculture for leafy greens, herbs, and certain fruiting crops, when powered by photonic solar electricity and illuminated by spectrally optimized LEDs, tuned to precisely the wavelengths that drive photosynthesis most efficiently. Vertical farms produce year-round yields with 95% less water than field agriculture, zero pesticide use, and supply chains measured in kilometers rather than thousands of kilometers. Photonic hyperspectral imaging systems monitor plant health at the cellular level, detecting nutrient deficiencies, disease onset, and stress responses before they are visible to the human eye, enabling precision interventions that optimize yield and quality while minimizing resource inputs. Rooftop aquaponics systems integrate fish aquaculture with hydroponic plant production in closed nutrient loops, Fish waste provides nutrients for plant growth. Plants purify the water that returns to the fish tanks, and the system produces both protein and vegetables with minimal external inputs. Insect protein production facilities convert food waste and crop residues into high-quality protein through the cultivation of black soldier, fly larvae or mealworms. At land and water intensities orders of magnitude lower than conventional livestock agriculture, community gardens, urban orchards, and edible streetscapes integrate food production into the public realm, providing fresh produce, ecological function, and community cohesion simultaneously. Waste in the circular economy, zero waste by design. The Photonic City is designed around the principle that waste is a design failure, evidence that materials and energy are being allowed to leak out of the urban system rather than being cycled continuously. The goal is not waste management but waste elimination, achieved through the application of circular economy principles at every scale from product design to urban infrastructure planning. Extended producer responsibility legislation requires manufacturers selling products in the Photonic City to take financial and physical responsibility for those products at end of life, creating powerful incentives for design for disassembly, material efficiency, and recyclability. Digital product passports, blockchain records maintained on the city's photonic computing infrastructure, track the material composition, ownership history, and end-of-life obligations of every significant product in the city, ensuring that materials can be efficiently recovered and returned to productive use when products are retired. Photonic sorting robots in the city's material recovery facilities use AI-powered machine vision running on photonic computing hardware to identify and separate material streams with accuracy above 99%, processing mixed waste at speeds and volumes that manual or conventional automated sorting cannot approach. Chemical recycling facilities powered by photonic solar electricity convert plastic waste that cannot be mechanically recycled into virgin quality monomers for new plastic production. Plasma gasification units convert residual organic waste, the fraction that cannot be composted, recycled, or otherwise recovered, to syngas for electricity generation, approaching the goal of zero landfill disposal. Governance, equity, and social systems. Photonic civic infrastructure. The abundance of clean energy and distributed computing capacity in the Photonic City creates the material foundation for a more equitable and participatory urban governance model. When energy is essentially free, produced in excess by the city's photonic infrastructure, it cannot be a source of poverty or exclusion. Universal basic energy, providing every resident with sufficient clean electricity for lighting, heating, cooling, cooking, and digital connectivity at no charge, eliminates energy poverty as a dimension of urban inequality. The economic value of the city's excess energy generation, fed to the regional grid, can fund public services and infrastructure, creating a virtuous cycle in which photonic abundance underpins social equity. The city's photonic computing infrastructure supports new models of democratic participation and transparent governance. Real-time participatory budgeting platforms allow residents to direct portions of the city's discretionary spending toward priorities they identify, with the digital twin providing immediate visual feedback on the projected impact of different spending choices. AI-assisted policy simulation tests proposed regulations and interventions in the virtual city before implementing them physically, reducing the risk of unintended consequences and building public confidence in evidence-based decision-making. Transparent, tamper-proof ledger systems running on the photonic computing fabric provide citizens with verifiable records of government actions, procurement decisions, and environmental performance, supporting accountability and trust. Health and well-being by design. The Photonic City treats human health and well-being not as outcomes to be managed by healthcare systems, but as properties to be designed into the urban environment. Clean air, enabled by the elimination of fossil fuel combustion and the filtration and cooling effects of abundant urban vegetation, dramatically reduces the burden of respiratory and cardiovascular disease that conventional cities impose on their residents. Active transport infrastructure that makes walking and cycling the most convenient modes of urban movement embeds physical activity into daily life, reducing the burden of sedentary lifestyle diseases. Biophilic design that integrates nature into every scale of the built environment, from the view from a window to the character of a neighborhood, reduces chronic stress and mental health burdens. Dark skylighting design, acoustic refuges, and the elimination of the noise and visual chaos of car-dominated streets restore the sensory environments that human nervous systems evolved in and that dense conventional cities systematically destroy. Exemplars in the path forward, cities leading the transition. Several cities around the world are already demonstrating elements of the photonic sustainable city vision, providing proof of concept for its core components. Copenhagen has achieved carbon neutrality for its electricity supply and is targeting net zero carbon across all sectors by 2025, driven by offshore wind, district heating, and cycling infrastructure that accommodates more than 60% of all trips to work and education. Masdar City in the UAE, while smaller in scale and still incomplete, demonstrates purpose-built zero-carbon urban design in a harsh desert climate, powered entirely by solar and wind energy. Songdo in South Korea has deployed citywide pneumatic waste collection, comprehensive sensor networks, and integrated building management systems that demonstrate the potential of sensor-integrated urban infrastructure. Singapore has pioneered vertical greening, integrated water management, and photovoltaic deployment at urban density in a tropical climate, demonstrating that sustainability and urban vitality are compatible. None of these cities yet integrates the full photonic energy and computing vision described in this essay. The complete photonic city, with photonic solar on every surface, distributed optical computing embedded in the energy infrastructure, real-time digital twin governance, closed-loop water and food systems, and zero-waste circular economy, remains a design target rather than a completed achievement. But each of its components has been demonstrated at meaningful scale, the underlying technologies are advancing rapidly, and the economic case for the integrated vision is becoming compelling as the cost of photonic solar, solid-state batteries, photonic computing chips, and precision agriculture technologies continue to fall. The sustainable city powered by photonic energy and computing systems is not a utopian fantasy, but a technically achievable design target, one whose components are increasingly available and whose economics are increasingly favorable. It is a city in which every surface generates energy, every wasted photon performs computation, every material cycles continuously, every drop of water is recaptured and purified, and every resident lives in an environment of clean air, accessible nature, and genuine abundance, not despite the constraints of sustainability, but because of them. The deepest insight of the photonic city vision is that sustainability and quality of life are not in tension, they are the same thing, approached from different directions. A city that runs on sunlight, computes with light, grows food on its rooftops, moves its people on bicycles and electric trains, and cycles its materials indefinitely is not a city of sacrifice and constraint. It is a city that has simply stopped wasting energy, wasting materials, wasting human potential on traffic and pollution and preventable disease. The photonic technologies that make such a city possible are not just engineering tools, they are the means by which human civilization can finally build urban environments worthy of the intelligence and creativity of the people who inhabit them. The question is not whether such cities are possible, they are. The question is how quickly we choose to build them. What are the most efficient photonic energy systems and technologies to create the most sustainable and regenerative future? This is the frontier where photonics, energy, ecology, and computation converge at their most ambitious. Here's a comprehensive map. The efficiency hierarchy of photonic energy technologies. Tier 1, highest efficiency. Multi-junction photonic solar cells 3V semiconductor stacks, gain GaAsja, with photonic crystal interlayers. Each junction captures a different spectral band current record. 47.6% under concentrated light, NREL, 2023, with photonic crystal optimization, projected 55 to 60% used in satellites and concentrating solar power today. Thermophotovoltaic, TPV systems. A thermal emitter heated to 1000 to 2000 degrees Celsius re-radiates photons at a specific wavelength. Photonic crystal emitter filters emission to exactly match a PV cell's band gap, converts heat from any source, solar, industrial waste heat, nuclear decay, to electricity. MIT demonstrated 40% efficiency in 2022, higher than any heat engine at small scale can run 24/7 using stored heat, solving solar intermittency at its root. Photonic luminescent solar concentrators. Quantum.LSC waveguides with near-unity quantum yield stack spectral layers for broadband capture, can cover entire building facades and windows, generate power from diffuse light, cloudy skies, and indirect angles. Tier 2, high efficiency plus scalability. Perovskite silicon photonic tandems. Best current lab result, 33.7% certified. Lunges, 2024. Photonic crystal texturing at the perovskite silicon interface optimizes light management, manufacturable via roll-to-roll printing for large area deployment. Projected commercial efficiency, 35 to 38% within 5 years. Concentrating photovoltaic with photonic optics. Fresnel lenses or parabolic mirrors focus sunlight 500 to 1000x onto tiny multi-junction cells. Photonic anti-reflection coatings and spectral filters maximize conversion, combined with thermal capture of excess heat. Total energy utilization 70% best suited for high direct normal irradiance regions, deserts, high altitudes. Solar thermochemical energy storage. Concentrating solar heat's a thermochemical reaction, e.g., calcium oxide, calcium hydroxide. Energy stored indefinitely in chemical bonds, no thermal loss over time, released on demand as heat for TPV generation or industrial processes. Effectively provides 24/7 solar energy without batteries. Tier 3, transformative long-term, hot carrier solar cells. Capture electrons before they thermalize, lose energy as heat, requires photonic nanostructures to slow carrier cooling. Theoretical efficiency, 66% for single junction, currently at 20% in lab. Material science is the bottleneck. Singlet fission solar cells. Organic molecules split one high-energy photon into two usable lower-energy photons. Dramatically improves UV utilization. Can be applied as a coating on existing silicon panels. Plus 30% current boost. Theoretically, Cambridge and MIT leading research. Photon recycling architectures. In ultra-high-quality semiconductors, GAAs, re-emitted photons are reabsorbed, creates a photon recycling loop that approaches thermodynamic limits combined with photonic mirror systems. Theoretical ceiling 85%, currently demonstrated at 29%, but roadmap to 40% plus is clear. Space-based solar power. Photovoltaic arrays in geostationary orbit collect unfiltered solar radiation. 24/7 energy transmitted to Earth via microwave or laser. Photonic beam, no atmosphere, no night, no weather, 8x more solar energy available than ground-based. Japan, JAXA, NESA targeting demonstrations by 2030s. Photonic energy storage technologies. Storage is the critical complemented generation. These are the photonic approaches: all optical energy storage, photonic crystal thermal batteries, phase change materials, silicon, salt mixtures, store heat at 400 degrees C plus photonic crystal surfaces, optimize absorption and emission spectra and Tora energy. And fourth, power building commercial systems, now energy density 5-10x higher than lithium ion at fraction of the cost. Thermophotovoltaic round-trip storage, charge, electric resistance, heating of graphite, thermal mass discharge. TPV cell converts thermal radiation back to electricity. Round-trip efficiency now reaching 44%. Mid-Google Alphabet small to project, scales to grid level using cheap, abundant materials. Photon-assisted chemical storage, solar hydrogen via photocatalysis, semiconductor photocatalysts, titanium dioxide, gallium nitride, split water using sunlight directly, no electrolyzer needed. Photonic nanostructuring increases surface area and light absorption. Theoretical solar to hydrogen efficiency, 30% plus, current lab, 20%, produces storable, transportable clean fuel directly from sunlight and water. Artificial photosynthesis. Biomimetic systems replicate plant photosynthesis to produce liquid fuels or hydrogen. Photonic antenna complexes, like chlorophyll arrays, absorb broadband light, convert CO2 plus H2O hydrocarbons using solar energy. Net negative carbon when coupled with atmospheric CO2 capture. Joule unlimited and Heliogen leading commercial development. Photonic systems for energy beyond solar. Photonics isn't limited to solar, it enables radical efficiency in other energy domains. Photonic radiative cooling. Specially designed photonic surfaces emit heat directly to outer space, at 3K, through the atmospheric transparency window, achieves cooling below ambient air temperature, with zero electricity, can reduce building cooling loads by 60 to 70% in hot climates, combines with solar panels to passively cool them, improving efficiency by 5 to 8%. Thermophotonic systems for waste heat recovery. Industrial processes, steel, glass, cement, waste enormous amounts of heat as infrared radiation. Photonic crystal coatings on industrial surfaces convert this radiation to electricity via TPV. Could recover 15 to 25% of all industrial waste heat globally, equivalent to hundreds of gigawatts. Photonic thermoelectric generators. Nanostructured thermoelectric materials with photonic phonon engineering achieve higher ZT efficiency values, convert temperature gradients, geothermal, oceanic thermal, waste heat, to electricity. New photonic metamaterial designs pushing ZT above 3.0 versus 1.0 for conventional materials. Nuclear photovoltaics, betavoltaics. Radioactive isotopes emit beta particles that generate photons, and a scintillator photovoltaic cell converts those photons to electricity. Extremely long-lived, decades, high energy density ideal for deep space, remote sensors, and medical implants. The regenerative systems vision. The most efficient photonic energy future isn't just about conversion percentages, it's about closed-loop regenerative systems where energy, matter, and information cycle continuously. Sunlight from photonic multi-junction harvest generates electricity, then TPV thermal storage provides 24/7 baseload power. Photonic computing fabric has zero-cost AI, sensing, control. Artificial photosynthesis produces fuel, food, and removes carbon. Radiative cooling is for passive thermal management. Photonic sorting and recycling includes zero-waste material cycles in order to push back to healthy ecosystems for a regenerative biosphere. Every wasted photon performs work. Every waste stream becomes a resource. Every system monitors and optimizes itself. The result is an energy civilization that doesn't just sustain itself, it actively restores the natural systems it depends upon. The 5 principles of the photonic regenerative future. Full spectrum utilization. Every photon does work, whether converted to electricity, stored as heat, used for computation, or deployed for photocatalysis. Temporal continuity. Thermochemical and TPV storage deliver solar energy 24/7, eliminating the day-night limitation. Material closure. Photonic systems enable closed-loop recycling of every material, from rare earth elements in panels to nutrients in food systems. Embedded intelligence. Photonic computing embedded in energy infrastructure self-optimizes continuously with no additional energy cost. Ecosystem regeneration. Net negative carbon, net positive biodiversity, and atmospheric restoration are design requirements, not afterthoughts. The photonic energy future isn't an incremental improvement on fossil fuels. It is a fundamentally different relationship between human civilization and the physical world, one in which sunlight, intelligently managed by photonic systems, provides everything: energy, materials, food, water, computation, and the restoration of the living world. The most efficient photonic energy systems and technologies for a sustainable and regenerative future. Humanity stands at a singular inflection point in its relationship with energy. The fossil fuel civilization that powered the Industrial Revolution and the modern world has delivered extraordinary material prosperity while simultaneously destabilizing the atmospheric, oceanic, and ecological systems on which all life depends. The transition away from fossil fuels is no longer merely an environmental aspiration, it is a civilizational necessity. But the question of what replaces fossil fuels is not simply a matter of substituting one energy source for another. It is an opportunity to fundamentally reimagine how human civilization harvests, stores, distributes, and uses energy, and in doing so, to build not merely a sustainable civilization that holds steady at current levels of environmental impact, but a genuinely regenerative one that actively restores the natural systems that centuries of industrial activity have degraded. Photonic energy systems, technologies that harvest, manipulate, store, and convert light with engineered precision at the nanoscale, represent the most promising pathway to this regenerative future. They offer efficiency levels that conventional energy technologies cannot approach, storage solutions that eliminate the intermittency limitations of solar and wind, computing capabilities that turn the energy infrastructure itself into an intelligent network, and chemical conversion pathways that can produce fuel, food, and clean water directly from sunlight. This essay surveys the full landscape of photonic energy technologies, organized by their efficiency and transformative potential, and concludes with a synthesis of the principles that define a truly regenerative photonic energy civilization. The efficiency hierarchy, from proven to transformative. Multi-junction photonic solar cells. At the apex of currently demonstrated solar energy technology stand multi-junction photovoltaic cells, stacked assemblies of semiconductor layers, each engineered to absorb a specific portion of the solar spectrum with maximum efficiency. Where a single-junction silicon cell is constrained by the Shockley-Queisser limit to a theoretical maximum of approximately 29% efficiency, a multi-junction cell distributes the absorption task across multiple junctions with different band gaps, allowing far more of the solar spectrum to be captured at or near its thermodynamic limit. The current world record for solar cell efficiency, 47.6%, set under concentrated illumination, belongs to a 4-junction 3V semiconductor device incorporating gallium indium phosphide, gallium arsenide, and germanium layers. The integration of photonic crystal interlayers between the junctions of these cells represents the next frontier in multi-junction performance. Photonic crystals engineered at the nanoscale can be designed to reflect specific wavelengths back into the junction above while transmitting others to the junction below. acting as perfect spectral beam splitters that ensure each photon reaches the junction where it will be most efficiently converted. They can also enhance light trapping within each junction, increasing the effective optical path length and absorption probability for photons near the junction's band gap edge. Modeling of optimized multi-junction cells with photonic crystal interlayers and light management projects efficiencies of 55 to 60% under concentration, more than double the performance of commercial silicon panels. These cells are currently used primarily in space satellites and concentrating solar power systems, where their high cost per unit area is justified by the premium value of power in space or the ability of concentrating optics to illuminate a small cell area with the light collected from a large mirror or lens area. As fabrication costs fall through advances in epitaxial growth, nanoimprint lithography, and materials science, multi-junction photonic cells are expected to become economically viable for a widening range of terrestrial applications. Thermophotovoltaic systems. Thermophotovoltaics represent one of the most conceptually elegant and practically significant developments in photonic energy technology of the past decade. A thermophotovoltaic system consists of a thermal emitter, a material heated to temperatures between 1000 and 2000 degrees Celsius, that radiates photons at wavelengths determined by its temperature and surface properties, and a photovoltaic cell that converts those photons to electricity. The critical innovation is the use of photonic crystal surfaces on the thermal emitter to tailor its emission spectrum precisely to the band gap of the photovoltaic cell, ensuring that virtually all emitted photons are energetically matched to the cell in that sub-band gap radiation, which would be wasted in a conventional TPV system, is reflected back to the emitter to maintain its temperature. In 2022, researchers at MIT demonstrated a thermophotovoltaic system achieving 40% efficiency, a landmark result that exceeded the efficiency of any conventional heat engine operating at comparable scale. The theoretical efficiency of optimized TPV systems with photonic crystal emitters approaches 60%, and the roadmap to achieving this is increasingly clear. What makes TPV systems transformative for a regenerative energy future is not merely their efficiency but their versatility. They can convert heat from any source, solar thermal collectors, industrial waste heat, geothermal energy, nuclear decay, or stored thermal energy, to electricity with equal facility. This universality, combined with the ability to store thermal energy cheaply in densely and phase-change materials or thermochemical systems and discharge it through TPV cells on demand, offers a solution to the intermittency problem of solar energy that does not require rare materials, electrochemical degradation-prone batteries, or geographically constrained hydroelectric storage. Perovskite silicon photonic tandem cells. For large area, cost-competitive solar energy generation at the scale required to power cities and nations, perovskite silicon tandem cells with photonic light management represent the most mature and rapidly advancing high-efficiency technology. The perovskite top cell, with its tunable bandgap and high absorption coefficient, captures the high-energy visible portion of the solar spectrum. The silicon bottom cell captures the near-infrared photons transmitted through the perovskite. The photonic interface between the two cells, a textured, nanostructured surface that scatters light to increase optical path length in both materials, ensures that the maximum possible fraction of incident photons is absorbed rather than transmitted or reflected. The certified efficiency record for perovskite silicon tandem cells reached 33.7% in 2024, already exceeding the practical efficiency of the best single-junction silicon cells and approaching the theoretical tandem limit. Commercial projections based on current improvement trajectories suggest that efficiencies of 35 to 38% will be achievable in manufacturing within 5 years. Crucially, perovskite layers can be deposited by solution processing, essentially printing, on top of existing silicon cell manufacturing lines, making the transition to tandem architectures less disruptive than a complete technology replacement. The combination of high efficiency, large area manufacturability, and compatibility with established silicon photovoltaic infrastructure makes perovskite photonic tandem cells the most likely technology to dominate the next generation of commercial solar installations. Concentrating photovoltaic systems with photonic optics. Concentrating photovoltaic systems use optical elements, Fresnel lenses, parabolic mirrors, or holographic diffraction gratings, to focus sunlight from a large collection area onto a small area of high-efficiency multi-junction photovoltaic cells. Concentration ratios of 500 to 1000 times are typical, dramatically reducing the area of expensive semiconductor material required per unit of energy generated. With photonic anti-reflection coatings on lens and mirror surfaces, photonic spectral filters that route different wavelengths to different cells in a split spectrum architecture, and thermal capture systems that recover the heat generated by photons above the cell's absorption threshold. Total solar energy utilization, the fraction of incident solar energy converted to useful electricity or heat, can approach 70%. The primary limitation of concentrating photovoltaic systems is their requirement for direct normal irradiance. They can only focus direct sunlight, not the diffuse scattered light that constitutes a significant fraction of solar irradiance in cloudy climates. This limits their deployment to high radiance regions, particularly deserts and high-altitude locations. In these regions, however, their combination of high efficiency and thermal cogeneration makes them among the most productive solar energy systems available. Long-term transformative technologies. Hot carrier solar cells. The most fundamental inefficiency in all conventional photovoltaic systems is thermalization. When a photon with energy above the semiconductor bandgap is absorbed, the excess energy above the bandgap is rapidly dissipated as heat within the semiconductor lattice, on a timescale of picoseconds. This thermalization process accounts for the largest single loss mechanism in solar cells, representing roughly 30% of total incident solar energy in a silicon cell. Hot carrier solar cells aim to extract the energetic electrons produced by high-energy photon absorption before they thermalize, capturing the excess energy as electrical work rather than allowing it to degrade to heat. Achieving hot carrier extraction requires photonic nanostructures that perform two simultaneous functions, slowing the rate of carrier phonon scattering within the absorber, the process by which hot electrons transfer their excess energy to the crystal lattice, and providing narrow bandwidth energy. Selective contacts that allow only carriers within a specific energy range to be extracted, preventing rethermalization at the contacts. Photonic crystal structures and quantum well architectures have been theoretically shown to enable both functions, and laboratory demonstrations have achieved meaningful hot carrier effects, though current device efficiencies remain around 20%. The theoretical efficiency limit for an optimized hot carrier cell is 66% for a single junction, more than double the Shockley-Queisser limit, and the roadmap to approaching this limit, while technically challenging, is increasingly well defined. Achieving hot carrier collection at practical efficiencies would represent the most significant advance in solar cell physics since the invention of the p-n junction. Singlet fission solar cells. Singlet fission is a quantum mechanical process that occurs in certain organic molecules in which the absorption of a single high-energy photon generates two excited electron states rather than one, in effect, splitting one photon into two usable excitations. This process, which occurs on femtosecond timescales in materials such as pentacene and tetracene, offers a pathway to harvesting the ultraviolet and high-energy visible portions of the solar spectrum with dramatically improved efficiency. Applied as a molecular coating on the front surface of a conventional silicon solar cell, a singlet fission layer could in principle boost the photocurrent generated by high-energy photons by up to 30%, without any modification to the underlying cell. The engineering challenge is transferring the two excitations generated by singlet fission efficiently to the silicon cell below, a process that requires careful management of energy levels at the organic and organic interface. Research groups at Cambridge, MIT, and Stanford have demonstrated singlet fission energy transfer to silicon with increasing efficiency, and the combination of singlet fission layers with photonic anti-reflection in light trapping structures is expected to enable practical efficiency boosts in commercial panels within the next decade. Photon recycling architectures. In the highest quality semiconductor materials, particularly gallium arsenide, photons emitted by radiative recombination of electron-hole pairs within the material have a significant probability of being reabsorbed before escaping, a process called photon recycling. In an optimized photon recycling architecture, photonic mirror systems surrounding the solar cell reflect virtually all emitted photons back into the absorber, creating a recycling loop in which photons contribute multiple absorption events before finally being collected as electrical current or lost to unavoidable emission. This recycling effectively raises the quasi-Fermi level splitting in the cell, increasing the open circuit voltage, and allows the cell to approach the thermodynamic limit of solar energy conversion more closely than any other single junction architecture. The theoretical efficiency of a perfect photon recycling solar cell approaches 85% under maximum concentration, a figure that would transform the economics of solar energy if achievable in practice. Current gallium arsenide cells with photon recycling have demonstrated efficiencies of around 29%, and the path to higher efficiencies requires improvements in material quality, optical confinement, and contact design that are the subject of intensive ongoing research. Space-based solar power. The ultimate expression of photonic solar energy harvesting is the collection of solar energy in space, where there is no atmosphere to absorb and scatter radiation, no nighttime interruption, and no weather variability, conditions that make the available solar resource approximately 8 times larger per unit area than on Earth's surface, continuously available around the clock and throughout the year. Space-based solar power systems would deploy large photovoltaic arrays in geostationary orbit, converting sunlight to electricity with high-efficiency multi-junction photonic cells, and transmit the generated power to Earth's surface via highly collimated microwave or laser beams, a photonic power transmission technology that converts electricity back to electromagnetic radiation for transmission through the atmosphere and reconverts it to electricity at ground-based receiving stations. The technical feasibility of space-based solar power has been established by decades of analysis and, increasingly, by hardware demonstrations. The Japanese Aerospace Exploration Agency has been developing space-based solar power technology for decades and is targeting a demonstration mission in the 2030s. The European Space Agency and several national programs are pursuing parallel development efforts. The primary barriers are the cost of launching sufficient mass to orbit and the efficiency of wireless power transmission. Advances in lightweight photonic solar cells, high-efficiency laser or microwave transmitters, and reusable launch vehicles are progressively reducing these barriers, and space-based solar power is widely projected to become economically competitive within the second half of this century. Photonic energy storage. Energy storage is the essential complement to photonic energy generation, transforming the intermittent output of solar systems into the continuous, reliable supply that civilization requires. Photonic technologies offer storage solutions at every scale, from building-level thermal batteries to grid-scale thermochemical systems. Thermophotovoltaic thermal batteries. The pairing of thermal energy storage with thermophotovoltaic conversion represents one of the most promising grid-scale energy storage technologies currently under development. The charging process uses electricity from solar panels during periods of excess generation to resistively heat a thermal mass of graphite, ceramic, or high-temperature molten material to temperatures above 1,500 degrees Celsius. This thermal energy can be stored for extended periods with minimal loss, as the thermal mass is well insulated and radiative losses at high temperature are managed by photonic surface coatings. The discharging process uses thermophotovoltaic cells to convert the thermal radiation emitted by the hot thermal mass back to electricity on demand. Companies including Antora Energy, Rondo Energy, and Fourth Power are developing commercial systems based on this principle, targeting round-trip efficiencies of 40 to 55% at cost per kilowatt-hour of storage that are dramatically lower than lithium-ion batteries, achievable because the thermal mass is simply high-grade graphite or industrial ceramics, abundant and inexpensive materials requiring no rare metals or complex electrochemistry. At grid scale, thermophotovoltaic thermal batteries could store days or weeks of renewable energy generation, providing the long-duration storage needed to fully decarbonize electricity systems that must maintain reliability through extended periods of low solar and wind generation. Solar thermochemical energy storage. Thermochemical energy storage takes the concept of thermal batteries further by storing energy in the chemical bonds of reversible reactions rather than as sensible or latent heat. Certain chemical reactions, including the dehydration of calcium hydroxide to calcium oxide, the reduction of metal oxides, and the decomposition of ammonia, absorb large amounts of thermal energy when driven forward by concentrated solar heat and release that energy with high fidelity when reversed. Because the energy is stored in chemical bonds rather than as heat, there is virtually no thermal loss over time, regardless of storage duration. A thermochemical energy store charged in summer can in principle release its stored solar energy in winter with negligible degradation, a capability that no conventional battery or thermal storage system can match. When the thermal energy released by thermochemical storage is converted to electricity through thermophotovoltaic cells with photonic crystal emitters, the complete system, solar collection, thermochemical storage, TPV conversion, constitutes a solar energy system that delivers firm, dispatchable electricity around the clock, in all seasons, using no fossil fuels, no electrochemical batteries, and no geographically constrained hydroelectric infrastructure. Artificial photosynthesis and solar fuels. Nature solved the problem of solar energy storage 3 billion years ago through photosynthesis, the biological process by which plants, algae, and cyanobacteria use sunlight to split water molecules and reduce carbon dioxide. to carbohydrates, storing solar energy in the chemical bonds of organic molecules that remain stable for indefinite periods. Artificial photosynthesis aims to replicate and surpass this process using engineered photonic and catalytic systems, producing hydrogen, hydrocarbons, or other energy-dense chemicals directly from sunlight, water, and carbon dioxide. The photonic component of artificial photosynthesis consists of light harvesting antenna complexes, arrays of chromophore molecules, or quantum dots that absorb sunlight across the visible spectrum and funnel the resulting excited states to catalytic reaction centers with high efficiency, mimicking the architecture of natural photosynthetic antenna systems. At the reaction centers, catalysts, increasingly based on abundant, inexpensive metals rather than the platinum group metals of earlier research, perform the water splitting and carbon dioxide reduction reactions that store the harvested solar energy in chemical bonds. Laboratory demonstrations of artificial photosynthesis systems have achieved solar to hydrogen efficiencies approaching 20%, and theoretical analysis projects that optimized systems could reach 30% or higher. The implications for a regenerative energy future are profound. An artificial photosynthesis system producing hydrogen or liquid hydrocarbons from sunlight, water, and atmospheric carbon dioxide is not merely carbon neutral, it is net negative, actively removing carbon dioxide from the atmosphere while producing storable, transportable energy carriers that can fuel existing industrial processes, aviation, and shipping without requiring complete infrastructure replacement. At sufficient scale, such systems could simultaneously address energy security, carbon removal, and the production of sustainable chemical feedstocks for industry. Photonic systems for non-solar energy. Photonic radiative cooling. Radiative cooling is a passive thermal process in which a surface emits heat as infrared radiation directly to outer space through the atmospheric transparency window, the range of wavelengths between 8 and 13 micrometers at which the atmosphere is partially transparent to outgoing radiation. Under nighttime conditions, all surfaces undergo radiative cooling. The innovation of photonic radiative cooling is the engineering of surface structures that emit strongly in the atmospheric window while reflecting sunlight almost perfectly, allowing the surface to cool below ambient air temperature even under direct midday sunlight, without any energy input. Photonic radiative cooling surfaces, fabricated as multi-layer stacks of silicon dioxide, hafnium dioxide, and other dielectric materials with thicknesses engineered to create destructive interference for solar wavelengths and constructive interference for mid-infrared emission, have been demonstrated to cool surfaces 8 to 12 degrees Celsius below ambient temperature under direct sunlight. Applied to building rooftops and facades, photonic radiative cooling coatings can reduce cooling energy demand by 60 to 70% in hot climates. Applied to the back surface of solar panels, they passively maintain panel temperatures well below the levels that degrade efficiency in conventional installations, improving energy yield by 5 to 8%. Applied to outdoor infrastructure, roads, vehicles, industrial equipment, they reduce the urban heat island effect that makes cities significantly warmer than surrounding rural areas, improving urban comfort and reducing city-wide cooling energy demand. Thermophotonic waste heat recovery. Industrial processes, the manufacture of steel, cement, glass, aluminum, and chemicals, operate at high temperatures and inevitably radiate large amounts of thermal energy as infrared radiation from hot surfaces, furnaces, kilns, and exhaust streams. Globally, industrial waste heat represents an energy resource comparable in magnitude to the total output of all nuclear power plants. Photonic crystal coatings on industrial surfaces can be designed to convert this waste radiation to electricity through thermophotovoltaic cells, recovering energy that currently serves no purpose. The efficiency of thermophotonic waste heat recovery depends on the temperature of the industrial source and the quality of spectral matching between the photonic emitter and the TPV cell. At steel mill temperatures above 1200 degrees Celsius, photonic crystal emitters can achieve spectral efficiencies approaching 80%, and overall system efficiencies of 20 to 30% for converting waste heat to electricity are achievable with current technology. Applied across the global industrial sector, thermophotonic waste heat recovery could generate hundreds of gigawatts of electricity from energy that is currently wasted, at near zero fuel cost and with minimal land footprint. Photonic enhancement of thermoelectric generation. Thermoelectric generators convert temperature gradients directly to electricity through the Seebeck effect, with no moving parts and in any size from milliwatts to megawatts. Their appeal lies in their versatility. They can harvest thermal energy from geothermal sources, oceanic thermal gradients, industrial exhaust streams, and even the temperature difference between a human body and ambient air. Their limitation has been low efficiency, characterized by a figure of Mach-Zehnder that rarely exceeds 1.0 in conventional materials. Photonic and phononic nanostructuring of thermoelectric materials offers a pathway to dramatically higher ZT values by independently manipulating electron transport and phonon, heat, transport within the material. Nanostructured interfaces scatter phonons, reducing thermal conductivity and improving the temperature gradient across the device, while leaving electron mobility largely unaffected, decoupling properties that are normally interlinked. Recent demonstrations of photonic metamaterial thermoelectric structures have achieved ZT values above 3.0, corresponding to efficiencies competitive with conventional heat engines. At ZT values above 4.0, thermoelectric generators would become practical for a wide range of waste heat and renewable thermal energy harvesting applications, transforming a currently niche technology into a mainstream energy resource. The integrated regenerative system. The technologies surveyed above are most powerful not as isolated innovations, but as components of an integrated regenerative energy system, in which every input is fully utilized, every waste stream becomes a resource, and the operation of the energy system actively restores rather than degrades the natural environment. The architecture of this integrated system begins with the sun. Multi-junction photonic solar cells, with concentrating optics, capture 50 to 60% of incident solar energy as electricity during daylight hours. Singlet fission coatings on panel surfaces boost the harvesting of high-energy photons. Photonic radiative cooling layers on panel rear surfaces maintain low operating temperatures, improving efficiency and longevity. Artificial photosynthesis systems co-located with solar arrays use some of the harvested electricity, or direct photons through photocatalytic pathways, to split water and reduce carbon dioxide, producing hydrogen and hydrocarbon fuels that store solar energy in chemical form for use at night, in winter, or in energy-intensive industrial and transport applications. Thermophotovoltaic thermal batteries store excess daytime electricity generation as high-temperature thermal energy, discharging through photonic crystal TPV cells to provide from overnight and seasonal power supply. The electricity and fuels produced by this system power cities, whose buildings are wrapped in perovskite silicon tandem panels and luminescent solar concentrator glazing, generating additional electricity from every surface. Photonic computing chips embedded in the solar infrastructure process the enormous streams of data generated by the city's sensor networks, monitoring energy flows, environmental quality, infrastructure health, and resource consumption, at near zero marginal energy cost, using photons that the solar cells cannot efficiently convert to electricity. Thermophotonic coatings on industrial facilities recover waste heat as additional electricity. Photonic radiative cooling surfaces on rooftops and roads reduce the urban heat island and cut cooling energy demand. The carbon dioxide absorbed by artificial photosynthesis systems and the carbon sequestered in bioture-amended soils, photosynthetic urban agriculture, and restored ecosystems around the city create a net negative carbon footprint. The water produced as a byproduct of hydrogen fuel cells, recovered from atmospheric moisture harvesting by photonic humidity sensors, and recycled through photocatalytic purification systems closes the water loop. The materials in the city's products and infrastructure are tracked through digital product passports maintained on the photonic computing fabric, ensuring that every material is recovered and returned to productive use at end of life. The result is an energy civilization that is not merely sustainable, stable at current levels of environmental impact, but genuinely regenerative, one whose operation actively improves the state of the natural world. The atmosphere cools as artificial photosynthesis removes carbon dioxide and fossil fuel combustion ceases. Ecosystems recover as land previously used for fossil fuel extraction, combustion infrastructure, and waste disposal is freed for restoration. Biodiversity recovers as the chemical, thermal, and noise pollution associated with conventional energy systems diminishes. The 5 principles of the photonic regenerative energy future. Full spectrum utilization. The sun delivers energy across the full electromagnetic spectrum, from ultraviolet to far infrared. A regenerative photonic energy system extracts useful work from every portion of this spectrum. Multi-junction cells and singlet fission layers harvest ultraviolet and visible photons. Near-infrared photons drive artificial photosynthesis. Mid-infrared radiation is managed by photonic radiative cooling surfaces, and excess thermal energy at all wavelengths is converted by thermophotovoltaic systems. The ideal of full spectrum utilization, in which no photon arrives at a photonic energy system and leaves without having done work, is the organizing principle of photonic energy engineering. Temporal continuity solar energy is intermittent on diurnal and seasonal timescales. A regenerative photonic energy civilization eliminates this intermittency not through geographic averaging of variable renewable output or through the deployment of fossil fuel backup generation, but through the conversion of solar energy to storable forms, thermochemical bonds, high-temperature thermal mass, hydrogen, liquid hydrocarbons, that can be held indefinitely and released on demand. Thermophotovoltaic conversion of stored thermal energy completes the cycle, delivering firm, dispatchable electricity from stored solar energy with efficiencies that competing storage technologies cannot match. Material closure. A regenerative energy system uses materials that are abundant, non-toxic, and fully recyclable, and operates processes that return materials to the natural environment in forms that support rather than degrade ecological function. Photonic energy technologies are increasingly meeting this standard. Silicon, the basis of most photovoltaic cells, is the second most abundant element in Earth's crust. Photonic crystal structures are fabricated primarily from silicon dioxide and other abundant dielectrics. Thermochemical storage uses calcium oxide and similar Earth-abundant minerals. And artificial photosynthesis catalysts are being engineered from iron, nickel, and manganese rather than rare and toxic platinum group metals. Embedded intelligence. The photonic computing infrastructure that runs on the city's solar energy systems provides the intelligence needed to optimize every element of the energy and material flows described above, predicting generation and demand, routing energy to its highest value use in real time, detecting and responding to faults and inefficiencies before they become failures, and continuously improving system performance through machine learning. This embedded intelligence is not an additional energy cost. It is powered by the photons that the energy system cannot otherwise use, making the computational capacity of the system a free co-product of its energy harvesting function. Ecosystem regeneration. The ultimate measure of a regenerative energy civilization is not its efficiency metrics or its carbon balance, but the health of the living world it inhabits and depends upon. A photonic regenerative energy system achieves net negative carbon emissions, eliminating the primary driver of climate disruption. It eliminates the air, water, and soil pollution of fossil fuel extraction and combustion, allowing ecological recovery. It requires far less land per unit of energy than fossil fuel systems, freeing land for ecosystem restoration. And its artificial photosynthesis systems actively accelerate the removal of excess carbon dioxide from the atmosphere, actively contributing to the restoration of the atmospheric chemistry on which all terrestrial life depends. The photonic energy technologies surveyed in this essay collectively describe a path from the fossil fuel civilization of the 20th century to a regenerative photonic civilization of the 21st and beyond. Multi-junction photonic solar cells, thermophotovoltaic systems, perovskite silicon tandems, hot carrier cells, singlet fission coatings, and space-based solar power constitute a hierarchy of increasingly powerful solar harvesting technologies whose combined deployment can supply all of humanity's energy needs many times over. Thermophotovoltaic thermal batteries, solar thermochemical storage, and artificial photosynthesis solve the intermittency and storability challenges that have limited the deployment of variable renewable energy. Photonic radiative cooling, thermophotonic waste heat recovery, and photonic thermoelectric generation extend photonic energy harvesting to thermal resources beyond direct solar radiation. And the photonic computing infrastructure embedded in the energy system provides the intelligence needed to operate the whole as a coherent, self-optimizing whole. What unites all of these technologies is a common orientation toward light as the fundamental resource of civilization. Sunlight has always been the primary energy source of the biosphere, the foundation on which all of Earth's ecosystems are built. For 2 centuries, industrial civilization diverted from this foundation, burning the accumulated solar energy of ancient geological ages stored in fossil fuels. The photonic energy revolution is, in the deepest sense, a return to the sun, but a return equipped with the tools of nanoscience, quantum physics, artificial intelligence, and synthetic biology that allow humanity to harvest solar energy with an efficiency and versatility that nature itself does not achieve. The regenerative future made possible by photonic energy systems is not a future of constraint and sacrifice. It is a future of extraordinary abundance, of energy too cheap and clean to meter, of computing embedded in the infrastructure of everyday life, of cities that breathe clean air and grow their own food, of industries that run on sunlight and return their materials to the cycle of use and reuse, and definitely, it is a future in which the operation of human civilization becomes indistinguishable, in its fundamental character, from the operation of the living world, drawing energy from the sun, cycling materials through closed loops, generating no net waste, and leaving the world more alive than it found it. That is what the most efficient photonic energy systems, fully realized, make possible. The physics is established, the technologies are advancing, the civilization remains to be built.